Hi guys, hi everyone. Thanks for coming. So I'm Danny Willems, cryptography engineer at o1Labs. So o1Labs incubated the Mina protocol. We also have been working on o1.js, which is a TypeScript framework that can be used to build a ZK app that is backed by our recursive layer called Pickles, and under the hood we use Kimchi, our REST library. And here today I'm gonna present you a work that we've been doing in the previous months that we call o1VM. So it's zkVM built for the MIPS architecture at the moment, but we can extend to other instruction set architectures in the future. It's initially for MIPS because it's a project that we've been working with Optimism, and we think in the future to integrate it also in Mina. What I'm going to talk about today, so I'm going to start by describing the design of the o1VM. I'm going to, after that, talk about the additive lookup or lookup, or I don't know how you want to call it, that we use to represent memory and register accesses. We call it RAMLookup. We also have a way to have, let's say, specialized instructions in our VM, and we implemented a version of Keccak using additive lookups, and also one way to represent Boolean operations using field additions. And also, I'll describe how we plan to support long traces using folding. Let's start by describing how the VM works. So you take any program written in any programming language, you compile it in the instruction set that you want. At the moment is the MIPS instruction set. And it creates a binary, and you're going to load this binary in the VM. We start by correctly setting the instruction pointer. And we start by going through the interpreter. The interpreter is going to be the piece of the o1VM that's going to build a witness that can be used after that to build the commitments and the accumulations for the cryptographic protocol. So how it does work, we first read the instruction pointer. We also read the next instruction pointer. We read the memory that's located at the given address given by the instruction pointer. We decode it. It's specific to the MIPS. And after that, we execute the instruction. And when we execute the instruction, it means that we're going to build constraints between different columns, and we're also going to perform some memory and register accesses, and we're going to use our lookup argument for this. So how does it look like? So we've got at the moment 93 columns. We have columns for the instruction pointer and pointer, the next instruction pointer, different columns for the decoding of the instruction. And also we've got a column to keep the index of the instruction counter, in the trace, which instruction, at which step we are at the moment. That's going to be used for the lookup argument. And also, we've got a way to communicate with other instruction. I'm not going to describe it. I'm not going to describe here. And also, for each instruction, we're going to have a certain set of columns, and that's going to be the one that is used by the lookup argument. Quickly about performances. At the moment, it's on consumer hardware on any laptop that you can run it. It's only CPU. It has a small RAM footprint at the moment, around 100 megabytes. And if you take the master branch of the o1Labs proof system repository, you're going to reach around 100 kilohertz. It means 100,000 instructions per second. And there are some open PRs that we've got to polish before merging. It was more a proof of concept. We realized that we were always inverting at each step a field element, which is useless. We can do it at the end. And so by doing that, we can get 1.7 megahertz by doing a batch inversion. And also, for the memory of the VM, at the moment is in master is a page index memory layout. It's not efficient at all to implement it like this. So by using a linear memory layout, we can use the CPU cache, and is gonna have far better performance, and it gives us on one laptop 6 megahertz for the witness generation. We also have other ideas to improve the witness generation, like using more linear structure in the code, using more the CPU cache, and also regarding commitments, most of the columns are only small values, and they have a certain shape, so we think that we can also improve the computation of the commitments. And also the commitments can be done in parallel of the other cores while we're building the witness. And to give you an idea on the kind of application of number of instructions for real-world application, for Optimism, we've got around 2.5 billion instructions. So let's describe how we perform memory access. So if you check at the lookup or additive lookup equations, you can see that it's an additive accumulation scheme, and you can see that the value that you look up, the value f very often in the paper, can be seen as a value that you add into an accumulator, and the table T that you look into can be seen as a value that you decrease from an accumulator. And therefore, we represent, when we want to overwrite a value into memory, we use a vector lookup. So when we want to override the memory cell X with the value Y, we have as I said, we've got a column where we keep the instruction counter. So tau is the instruction counter that I described before in the list of columns. And we also keep the last time that we access the value, and we also keep it in a column. And therefore, we simulate the fact that we overwrite a value by adding a certain value, and we remove from the accumulator when we read the whole value. And the same thing for reading a memory cell. We simulate the fact that we read the whole value at the previous step, and we overwrite with the current step. So how do we differentiate registers and memory? We use a table ID in the vector lookup, so we add, oops, it's the other button. So we add the table ID in the vector lookup. So R is a random combiner that you use. Beta is the evaluation point from the lookup, or lookup, or how do you want to call it? Is the evaluation point. We also have to do a range check on the instruction counter to be sure that we do not overwrite a value before that we do not read a value before we write into the memory. Also, all values that are included in the vector lookup are committed as commitments, as columns. And the verifier sends the random values, so the evaluation challenge, and also the random combiner after receiving the commitments of the columns. And also the initial and final memory are committed. That was for RAMLookup. So now let's talk about Keccak. So we implemented a version of Keccak using additive lookup, and also one way to implement Boolean operations using field addition. Our design is to have the whole Keccak permutation on one row. To have one row is equals to one permutation of Keccak. So we've got around 2,200 columns, 2,200 lookups, and around 900 constraints. And how do we do that? Is normally it's a 5 on 5 square, but yeah, it's 6 here. So the Keccak state can be seen as 25 values of 64 bits. What we do is we split each element of the state in 4 chunks of 16 bits, and we're going to expand. I'm going to get back a 64 bits value by inserting intermediary zeros, and these zeros are going to be used as carry values by the field addition. So how Keccak works is like most SPN construction. You've got a function that you repeat a few times over a certain state. So here, that's the construction of Keccak. You can see that it's always XOR operation or rotation or AND. And so what we want to do is we want to remove the XOR operation because you know it's very costly in circuit. You've got to decompose in bits, and after that you've got to do bit by bit operations. We don't want to do that. So what we want to do is we want to perform the field addition on the expansion of the 16-bit, as I showed you before. Everything is described in an RFC, is long, so I'm not going to describe it here in the talk. You also have the implementation there. And so, in a nutshell, how it works. If you've got 2 vectors, A and B, and you do the XOR on A and B, you can see that in blue, you're going to have, so in red and blue is the real bits of the expansion. So you've got here the 64 bits expansion. And when you do the addition on the same vector, you can see that at the same place, you're going to have the result of the XOR operation. And on the bit, on the left bit, you're going to have the result of the AND operation. So you can see that if you do 1 and 1, you're going to have 1, which is on the left. So it's a bit more complicated than that. Everything is in the RFC. Feel free to have a look. You've got all the different constraints that is described. And you also have the implementation. So regarding folding, you know that the programs is quite long. We've got 2.5 billion instructions to handle. So how do we want to do that? You can see instructions as a multivariate polynomial. So what we do is you can also see each instruction as a relation. Each instance is a folding instance. We split our trace in chunks of the same instruction, so we've got always the same circuit. We fold the n-1 for the I1 circuit, we fold the m-1 for the I2 circuit, and we combine after the 2 circuit by adding virtual selectors, and we do that for the whole trace. We also use a lookup argument, and also we reduce all polynomials to degree 2 at the moment. We also delay the multiscalar multiplication, and we also have a way to avoid doing the scalar multiplication and replace it only by doing elliptic curve addition and a lookup argument that I'm not going to describe here, but we can talk about that after on a piece of paper. I can draw it if you want. So, yeah. That's it. Thank you. We also hiring, so if you are interested in O1 Labs, we're doing cool stuff. So feel free to come. If you want to check the code, please check the code. You can check O1JS, Mina, and also the different RFCs that we try to write every time. So, yeah. That's it.